Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 8, Atomic Structure, Part 1. We are now in Chapter 7 of your textbook. Here are our objectives for today's video. Pause here. You do not need to draw this picture. So this chapter in general, we're going to be talking a lot about light. And then in order to understand light, we need to understand how waves work because light is primarily described as a wave. Sometimes it's not, but most of the time it is. A wave is just a massless transfer of energy. And when we're talking about waves, we're typically going to talk about the wavelength, which is the distance between crests, typically measured in meters or nanometers. The frequency, which is how often a crest, which is just the top of the wave, will hit a point in a given period of time. And that period of time is typically 1 second. So typically that will be measured in 1/seconds per second or hertz. And then in chemistry, we don't talk too much about amplitude, but in like a physics course, you would talk about amplitude. And then you're not going to need to use it too frequently, but crest just means the top of the wave, trowel just means the bottom of the wave. But in this class, we're primarily going to focus on the wavelength and the frequency of waves. Pause here. You do not need to draw the picture. We're specifically going to focus on one type of radiation, which is electromagnetic radiation, which is just the energy released by electromagnetic processes. When I say electromagnetic, I mean that it has something to do with matter. So you've talked about this a little bit last year when you took biology. You probably talked about visible light, why plants are green, all that sort of stuff. And visible light is just one small portion of the electromagnetic spectrum. What this picture is showing you is just the spectrum all the way on the left that has super high wavelength, all the way to over on the right where we have gamma radiation, super short wavelength, super high frequency. And then the images on the bottom are just giving you a context for how large the wave is. So a radio wave is approximately the size of a football field, whereas a single wave of gamma radiation is the size of an atomic nuclei, so extremely, extremely small. This is just sort of a reference table that we will be using. There's one in your textbook that I actually like a little bit more that we'll use for the problem set. Pause here. So in this chapter, we're going to need to be able to relate different quantities of a wave. So this equation here shows that wavelength, which we use that symbol, it's a lambda, it's a Greek letter, multiplied by frequency, which is at V, and it is equal to the speed of light, which is a constant. So if you don't already know how to put constants in your calculator, just remind me in class. I'll show you how to do it. It'll just make your life easier. So the wavelength times frequency is equal to the speed of light, 3.0 times 10 to the 8th. But that 3.0, that's not going to affect your sig figs for this. And what I see when I look at this equation is that wavelength and frequency are indirectly related to one another. Let's take a look at an example with this. Pause here and go ahead and try the example. All right. So the first thing that we're going to need to do is we are going to need to convert 780 nanometers to meters. And the reason why we have to do that is just to make the units work out, because C is in meters per second, not nanometers per second. Otherwise, the units wouldn't work out. Then we are going to solve for frequency. Just put that in your calculator. Be careful with your parentheses. And I got 3.8 times 10 to the 14th power, not to the negative. And then when it comes to things like frequency, it's pretty common to see them on the order of magnitude of 10 to the 14th power. So if I got an order of magnitude that didn't make sense, I would go ahead and put it in my calculator again. So anywhere between 10 to the 14th, 10 to the 15th is typically what you expect. It's not to say you could never have things that are outside of that range, but it is just very common to have them in this range just because of the range of frequencies associated with the electromagnetic spectrum. Pause here. So we talked about light as a wave, and I mentioned at the beginning of the video that sometimes we actually talk about it a little bit as a particle. So when we do talk about light as a particle, we refer to it as a photon. That is not to say that there are actual physical particles of light. It's when we are referring to light having some particle-like properties, because light has a dual nature, and we'll actually see in future videos that matter also has a dual nature. But in short, sometimes light does behave like a particle. When I say like a particle, what I mean is it sometimes has definite location. So when I think about waves, I think about indefinite location. They can be many places at once. You turn on a light, it illuminates the entire room. It doesn't just illuminate one small part of the room. But sometimes there is actual localized light. For example, when you get sunburned, there was definitely light on that exact spot on your skin when you got sunburned. And when we do refer to light as having definite location, we will call it a photon. When we need to calculate the energy of a photon, it is h, which is called Planck's constant, just named after the guy who made it, 6.626 times 10 to the negative 34th power. You could go ahead and put that in your calculator. Joules times seconds. That just makes sure that our final answer will be in joules when we calculate energy. Pause here. So for this, it's really just a straight up calculation. We'll be doing more with this in our future video. And I got 2.5 times 10 to the negative 15, 19th power. And that is in joules. So an order of magnitude anywhere between like 10 to the negative 17 to 10 to the negative 20 tends to make sense here. It's very low energy because it's literally a single photon, which is just one small unit. It's when we start talking about, say, moles of photons that you see orders of magnitudes that are higher than that. Okay, that's all for today's video. Thank you so much for watching and have a great night.